A sub n is a multiple of 23, and it's one more than a multiple of 2 to the nth power. And we're looking for a sub n's that are consecutive and equal to each other. Let's see if we can find some examples. Let's try n equals 1. We want this expression to be one more than a multiple of 2. This is solved when b is equal to 1. So we have a1 is equal to 23. Let's try n equals 2. This has to be one more than a multiple of 2 squared, or 4. Since 23 is one less than a multiple of 4, we can replace the 23 in this expression with negative 1. That makes b2 is equal to negative 1. In mod 4, that's 3. a2 then is 23 times 3, or 69. Let's try n equals 3, which means one more than a multiple of 2 cubed, or 8. Since 23 is one less than a multiple of 8, we can replace this expression with negative 1 times b3. That means b3 is equal to 7, and a3 is 23 times 7, or 161. For n equals 4, we're looking for multiples of 23 that are one more than a multiple of 16. In mod 16, 23 is equivalent to 7, so we'll do that substitution. Going through the multiples of 7, 7 times 7 is one more than a multiple of 16. So that gives us b4 is equal to 7, and a4 is equal to 161. And we have a3 is equal to a4. Let's stop now and try to generalize this. Again, we're looking for a multiple of 23 that's one more than a power of 2. Algebraically, we can write this as 23bn is a multiple of a power of 2 plus 1. Let's take the mod 23 equivalent of both sides. We have 0 on the left-hand side, and we'll isolate this term. So in mod 23, we have 2 to the n times cn is equivalent to negative 1. Let's see if we can look for a pattern in our powers of 2 in mod 23. When n is equal to 1, this is 2. We can multiply these residuals by 2 every time. We get 4 here. 2 cubed means we take the 4 and multiply by 2. We'll multiply this by 2 to get 16. 16 times 2 is 32. But to make this easier on us, we'll replace it with a 9. Multiplying 9 by 2, we get 18. Here we have 36, which is equivalent to 13 in mod 23. Multiplying by 2, we get 26, which is equivalent to 3. And then 6, 12, 24, which is one more than 23. And then when n equals 12, we start over again with a residual of 2. Each number in this column only depends on the number that came before it. So we're going to have a repeating pattern, repeating every 11 powers of 2. This means that if we have two numbers, 2 to the n, which will be the same as 2 to the x in mod 23, then that means n is going to be x more than a multiple of 11. Checking, we can do this substitution. This is 2 to the power of x plus 11y times cn, and we want this to be equal to negative 1 in mod 23. We notice from this line that 2 to the 11th power is equivalent to 1 in mod 23. So let's expand this exponent here. We can rewrite this as 2 to the 11th power raised to the y times 2 to the x. Since 2 to the 11th is equal to 1, 2 to the 11th raised to the y power is equivalent to 1 to the y power, which is 1. So I can replace this first factor with 1. So indeed, if 2 to the n is equivalent to negative 1, then 2 to the x, which came 11 before it, is also equivalent to negative 1. So what we're going to do now is check for consecutive equal values of a sub n in the first 11 powers of 2. And this is going to repeat, and we'll count those repetitions until n is equal to 1,000. Let's repeat our work from earlier with our power of 2 expression. So for n equals 1, this means 2c1 is negative 1 in mod 23. This gives us c1 is equal to 11, and a1 is 2 times 11 plus 1, or 23. Backing up, we see that that was the same answer we got in our example. So we'll continue with n equals 2. This gives us 4c2 is equal to negative 1. It might be helpful now to keep the multiples of 23 handy so we can compare them to our expression. I'll list them off to the right. Let's also keep track of our results as we go along in this table for n, cn, and an. Okay, so we're looking for a multiple of 4 that's one less than a multiple of 23, and we find it in 68. This gives us c2 is 17 and a2 is 69. For n equals 3, that's 2 cubed. We look for a multiple of 8 that's one less than a multiple of 23, and we find it in 160. This gives us C3 is equal to 20, and A3 is 161. These numbers ring a bell from our previous example, 69 and 161. So let's continue with n equals 4. We're looking for a multiple of 16. That's one less than a multiple of 23. Again, we find our answer in 161. This gives us a C4 of 10, and A4 is 161 again. And we'll go on to the fifth power of 2. 32 is the same as 9 in mod 23, so I'll replace that with 9. We'll look for multiples of 9 that are one less than a multiple of 23, and we find it in 45. This means C5 is equal to 5, and A5 is 161 again. Let's continue on with n equals 6. 64 is 5 less than 69, a multiple of 23, so I'll replace the 64 with minus 5, and we'll multiply both sides by -1. Adding 1 to each of these multiples of 23, we find that we get our answer when this expression is equal to 70. That means C6 is equal to 14, and A6 is 64 times 14 plus 1. This gives us 897. Going on to 128. 128 is 10 less than a multiple of 23, 138. So I'll place this with -10, C7, and multiply both sides by -1. Looking for multiples of 10 that are one more than these values, we find 70, which gives us C7 is equal to 7, and we'll calculate A7. That's 128 times 7 plus 1. We'll distribute 7 over 120 and 8, and then add 1. This gives us 897. And we have another pair of consecutive A's with the same value. Now we have 256. We'll subtract multiples of 230 to reduce this coefficient, and 26 is the same as 3 in mod 23. We'll subtract 1 from each of these multiples of 23, looking for a multiple of 3, and we find it in 45, which means C8 is equal to 15, and A8 is 256 times 15 plus 1. And multiplying this out, we get 3841. Just a few more left. Let's subtract some multiples of 23 from 512. We reduce this to 52C9. And then when we subtract 46, we get the equivalent 6C9 in mod 23. We'll subtract 1 again from each of these multiples of 23 to find a multiple of 6. Subtracting 1 from 115 gives us 114. And this is an even multiple of 6. So C9 is 19, and A9 is 512 times 19 plus 1, and this is 9729. And we'll continue with n equals 10, replacing these with smaller numbers by subtracting multiples of 23. And we'll subtract 92, and we get 12. But we might also want to replace 12 with -11 C10 because those multiples are easier to identify. And multiplying by -1, we're looking for multiples of 11 that are one more than a multiple of 23. We can use the alternating digit sum formula, and let's fill in some additional multiples of 23. Looking at 230, we notice that 231 is 11 times 21. So let's take C10 is equal to 21 and calculate A sub 10. This is 21,505. And we'll do n equals 11. Let's start by taking 2048 and subtracting multiples of 23 to get the smallest residual. We'll subtract 920 and subtract 920 again. 208 looks familiar, so we can subtract 207, and we find that 2048 is equivalent to 1. Actually, we had that earlier, didn't we? 2 to the 11th power was equivalent to 1. I could have just referred to this table. So C11 is equal to 22. So we'll calculate A11, which is 45057. Put this back in our table. Just in case, let's check n equals 12. Using our earlier table, 2 to the 12th power is equivalent to 2. Not surprisingly, it gives us the same solution for C12 as we had for C1. Checking our table, C1 is 11 and C12 is also 11. So everything is working out as planned. Let's calculate A12. We'll multiply 4096 by 11 and add 1. This is also 45057. Looking over our table, we find these three consecutive equal A sub n's. Here's another pair. And then A11 is going to be equal to A12. And this is going to repeat every 11 numbers until we get to n equals 1,000. Hate to do all this work and then mess up the counting, so I'm going to be extra careful here. One way to count is to start at 2 and count all the equivalent ANs in this interval of 11. In the interval between 2 and 12, 1, 2, 3, 4, we have 4 pairs of consecutive ANs. Adding 11 to each of these, in the interval between 13 and 23, we're going to have another 4 consecutive. The upper bound is always one more than a multiple of 11. Let's call this 11p plus 1. The lower bound is 11p minus 9. Let's see what's the highest value of p that has this interval. Our upper bound for n is 1,000. Solving for p, which goes up to 90. So our last full interval goes up to 991 from 981. And this is when p is equal to 90. So far, we're going to have 360 equivalent consecutive ANs. Now let's count the remainder between 992 and 1,000. Since 991 is one more than a multiple of 11, that's going to put us up here. Counting from 991, we'll find that a sub 993 is going to be equal to a sub 994. 994 is going to be the same as 995. 996 is going to be the same as 997. This is 998, 999, 1,000, so we don't need to count this last pair. So we have 3 more down here. So our total is going to be the 360 plus the 3 more, and our answer is 363. If you'd like me to solve any other contest problems, please leave them in the comments.